Hello, everyone. Welcome to today's seminar. It is my great pleasure to introduce today's speaker, Professor Rehan Kapadia from University of Southern California. Rehan is an assistant professor of electrical and computer engineering at USC, where he also holds the Colleen and Roberto Padovani Early Career Chair. Professor Kapadia is also the co-director of the newly formed Center for Integrated Electronics and Biological Organisms at USC. Rehan's research has been recognized by awards, including the Air Force Young Investigator Award, as well as the AVS Peter Mark Memorial Award. His research interest lies at the interface of material science and electrical engineering, with the aim of developing the next generation electronic and photonic devices for computing applications beyond CMOS. We're very excited to be able to learn more about his research in this area, but before I turn it over to Rehan, I would just like to remind our audience that you can ask your questions by either using the Q&A feature of the Zoom webinar by typing your question, or you can also at the end of the talk raise your hand and directly ask your question. So with that, Rehan, thank you for being here today. We're very excited to hear more about your great work. I turn it over to you.
Thank you so much, Farnaz, and thanks for the invitation and the opportunity to give a presentation of this seminar, the seminar series. So, just to kind of jump into things, what I'm going to be talking about today is kind of a broad overview of the two major topics that my group has been working on over the past few years, essentially. It's kind of two areas of work. The first area of work, what we're trying to do is we're trying to focus on how we can grow single crystalline materials, specifically compound semiconductors, how we can grow them non-epitaxially on oxides, nitrides, and metal substrates, with the goal of trying to enable a three-dimensional monolithic integration. And then taking those materials which we're growing and then making various devices out of that. So in today's talk, I'm mostly going to focus on our materials growth work, and I'll briefly flash some of the work that we're doing on devices. And then on another side of my group, we work on generating and using non-equilibrium electrons for what I call useful purposes. And in that area, we kind of have two different groups of projects. We have one group of projects where we are trying to use optically excited non-equilibrium electrons for electron emission devices. And on another side, we have electronically excited hot electrons for electrochemical applications. And I'm mostly going to focus on our work on optically driven devices for electron emission applications, and then just kind of quickly highlight some of our work on electrochemical devices. The work that I do here has kind of been funded by a variety of agencies, but mostly my materials and device work has been funded by SRC, NSF, NASA, JPL, and National Geospatial Agency. And then my work on non-equilibrium electrons has been heavily funded by Air Force, DOE, and I recently got some ONR funding as well for it. And my electrochemical hot electron electrochemistry work has been funded by SPR. And really, it's kind of because each of these areas kind of focuses on a different application. And, so to kind of jump into things, to talk about our materials and device work, I want to highlight something that I think most people here are somewhat familiar with, so I won't belabor the point, but we know that we're kind of living through two different paradigm shifts right now. First one being the end of lateral scaling. I think we all probably saw IBM's 2 nanometer technology announcement a couple of weeks ago, maybe a week ago. Basically we're getting to the point where we're not going to be able to improve computing power and computing performance through increases in density and speed of individual transistors. And at the same time, we happen to be living in this time where there's just an incredible amount of value that's being extracted from the use of AI and ML algorithms. basically analyze both structured and unstructured data. And so because of these two kind of, these two kind of paradigm shifts, there's some challenges that have popped up. One of which it happens to be this memory access challenge, where essentially as you in a traditional computing device, as you try to access larger and larger chunks of memory, and as you try to move data back and forth, larger and larger blocks of data back and forth, what ends up happening is that you just have to wait longer and longer time periods, driven by the type of memory that you need to access. So it's no longer controversial to say that future systems are very likely going to be tightly integrated, and they're going to be three-dimensional. However, because of this, because of this fact, what's going to end up happening is that if we say take a silicon substrate, silicon CMOS substrate, and we want to start building multiple layers of devices, especially at a large scale, what's going to end up happening is that you're not going to have epitaxial substrates on which to grow materials. So if we want to make multi-layer architectures, we're really left with two approaches. One is transfer-based approach, and the second where you grow a material and then you transfer to the substrate, or an amorphous or nanocrystalline material deposition approach. So if we take a quick look at heterogeneous integration and some of the challenges and some of the state-of-the-art approaches, really you have two choices here. One choice, what we can do is we can say, hey, let's take substrates of our desired material. Let's grow layers that we want on top of those substrates. Let's grow them epitaxially. They'll be really high quality. And let's just transfer them onto the desired device. This is actually a really great way of making high quality materials. And it's been explored by a lot of groups, including some groups at MIT who are doing fantastic work on it. And the advantages of this technology really center on how high quality the devices can be. There's still some challenges associated with actually scaling it to match silicon CMOS processing. So basically, most of these exotic devices that we want don't have 12-inch substrates, which means that you can't really get the advantages of scale of your silicon processing. And that's where a lot of the cost reduction really comes from when you get to this 300 millimeter type process, or eventually even larger. On the other side, you can do bottom-up epitaxial growth, where you just take a crystalline substrate and you just keep growing different types of materials on top of it. The challenge with that is you only have access to one crystalline crystalline surface, and so it makes it, as you start to get more and more complex, it makes it almost prohibitive to take this approach. So what we're trying to do is we're trying to say, hey, can we put a new tool in the toolkit here where we have bottom up a non-epitaxial crystalline material growth. So where you have your silicon device, you might have some oxides or nitride interposer, you might have some interconnects, and on top of that build a local crystalline materials. We're focusing on 3.5s. And so to address this challenge, in this first part of the talk, we're going to try to talk about three different main points. First is, can we grow crystalline semiconductors without an epitaxial template? Can the kinetics and thermodynamics of this growth allow us to actually make materials with reasonable performance at temperatures below 400 degrees C? And that temperature limit actually exists because of the fact that if we have a fabricated silicon CMOS wafer, we can't really process it at temperatures above 400 degrees C for too long. And so this thermal budget really limits what you can do and what temperatures and times you actually have access to if you want to build on top of a fully fabricated wafer. Now, it turns out that the challenge behind this, growing on non-epitaxial substrates, it can really be encapsulated by taking a look at these two SEM images here. They're SEM images of indium phosphide grown on molybdenum metal, so a non-epitaxial substrate. And the left-hand side, it's grown using close-space sublimation, and on the right-hand side, it's grown using MOCVD. Now, the thing about using these vapor phase growth techniques is you run into this limitation where the lateral grain size tends to be on the same order of magnitude as the thickness of the material. And that is because, and you can actually see that in these images. So this is a grain over here, this is a grain over here. And the reason for this is simply because you have your precursors coming in vapor phase. They react on your surface. They nucleate your desired material, but since there's no epitaxial template, it doesn't control the orientation of all of these relative nuclei. And then you don't have control over the geometry in which they're growing. And so essentially they'll grow in the vertical direction and the lateral direction, kind of, within an order of magnitude to the same rate. And so if you want, if you want nuclei that are spaced by 10 microns, in general, your film is going to be 10 microns thick before they merge. Now, what we were saying is, oh, well, what if we encapsulate it so we kind of control how thick these can grow, but then still let them grow out laterally, and then modify the growth conditions such that you only get a single nuclei in whatever area you want. So then that way you can define an area, grow the material such that you only get a single nuclei, and then have a single crystal domain of some size. And so the approach that we've taken for this is this templated liquid phase growth of 3,5s, where in this case, I'm showing an example of indium phosphide, where we take some substrate, so it's going to be silicon oxide, silicon nitride, titanium. We've done it with a whole bunch of different substrates. You deposit your group 3 metal, in this case indium, you cap it with the silicon dioxide cap, then you heat it up, and because it's capped with the silicon dioxide capping layer, even though the indium will turn to liquid at temperatures above about 160 degrees C, it stays in that original geometry. Then we start introducing, phosphorus to it. So we're going to indium phosphide. We introduce phosphorus to it, and what happens is, just like when you add salt to water, you supersaturate the water eventually, and salt crystals precipitate out. Here, we supersaturate the liquid indium, and indium phosphide precipitates out. And and you keep growing, and it consumes the template, and you're left with a single crystalline domain in your original template area. And if you look at some SEM images of how these materials grow, what you can see on the bottom here is that we have this indium template, and what we're showing is at different growth times how an indium phosphide crystal might nucleate and then start growing to consume the entire template. We can also kind of control the size and the shape. So for example, here I'm showing indium arsenide, and I'm showing a 60 micron circle of indium arsenide. You can also pattern it such that you get, more complex geometries. Here I'm showing an indium arsenide hull bar. So basically what happens is you pattern the desired geometry, and then you make, and then you just do a phase transformation to turn that pattern into your single crystalline domain. When we do this, we grow these materials, and so then for indium phosphide, we would do optoelectronic characterization. And one of the things that we're showing here is the indium phosphide, which we would grow on top of oxides and nitrides. 3 micron, 1 to 3 micron thick, or half a micron to 3 micron thick indium phosphide, versus a similarly doped crystalline indium phosphide wafer. And what we're doing is we're just comparing photoluminescence characteristics. So we're comparing our peak position, our full width half maximum. We're comparing the Urbach tail parameter, which is essentially what tells you, which is essentially the kind of gives you a sense of the disorder of the material. And finally, the quantitative photoluminescence, which tells you something about the relative rates of non-radiative recombination in the material. And what we see is that while it's not exactly the same, it's actually pretty close to a lot of these single crystalline wafers that you can buy. And what that tells us is that because we can grow single crystalline domains, even though it's non-epitaxial, we can actually start to achieve performance much better than what you could get if you just deposited a material using a standard vapor phase growth technique. Now, the challenge is that most of the stuff I've been talking about so far has been grown at maybe 500, 600, even up to 700 degrees C. And when you do that, what you actually get is pretty good quality material. And so that's what I'm showing here. We're showing some statistics of indium phosphide grown on non-epitaxial substrates as a function of temperature. And what you see is that if you look at the higher temperature materials, the peak position is pretty similar to what you might get from an indium phosphide wafer. the full width half maximum, again, pretty close to what you get from an indium phosphide wafer. Or about tail parameter is pretty good. But as you start to get lower and lower in temperature, closer to that kind of the holy grail of 400 degrees C, you get this divergence and the properties seem to get significantly worse. So that's not promising. However, what we found is that if you continue down and you actually get to drop down to about 300 degrees C or so, what ends up happening is that somehow, I'll say magically, even though it's not magically, somehow, quote unquote, magically, the properties of the material start to get better again. And by better, I mean the grown indium phosphide that's grown at about 300 degrees C on a non-epitaxial template starts to resemble our single crystalline wafer, starts to more strongly resemble our single crystalline wafer. And this was a puzzle for us, and you know, how we understand what's happening now is that the extrinsic defect density that's being incorporated at these lower temperature is lower, and that has to do with our capping layer, we think, because we use a substoichiometric silicon dioxide capping layer, which disproportionates to silicon plus silicon oxide SiO2. So anyway, the result of this is that we can actually get low temperature materials which look pretty good. So what we then said is, hey, well, let's look at, you know, say, for example, some indium arsenide material grown at 300 degrees C and take a look at the mobility of these materials. So what we would do is we take our substrate, we take an oxide substrate, we deposit some indium, we do a phase transformation into indium arsenide, and then we do a few further processing steps to kind of turn it into a useful substrate. But the thing that's kind of really interesting is that we grew a crystalline 3.5 on a non-epitaxial substrate in the geometry that we wanted, and our room temperature mobility for that material was about 5,900 or so. And the reason that that's really interesting is that if you think about what we typically get when we grow nanocrystalline materials at this scale, you get mobilities that are a couple of orders of magnitude lower. And so what this is really telling us is that we can grow low temperature crystalline semiconductors. We can grow it on a non-epitaxial substrate, and we can get what seems to be pretty good mobilities. Now, the thing is that when we looked at the, it's pretty good, but it's still not. I mean, it's not 40,000, right? Which is what you could potentially get with indium arsenide. But when we looked at the carrier density as a function of temperature here, what we actually found, which is pretty interesting, is that we even down to about 2 Kelvin, we didn't really see much of a change in this carrier density. And so what that was telling us is that our top and bottom surfaces of our indium arsenide were actually dominating the behavior of this device. And so actually, when we were measuring this, 6,000, this mobility of 6,000, what we're actually measuring was the surface mobility of this material. And so we did some modeling where we went in and we modeled the phonon scattering, surface roughness scattering, impurity scattering, and then we fitted our data using the surface roughness, our surface roughness scattering model, and that's what you see with these dashed lines. What we end up getting and what we end up seeing is that if we can reduce our surface roughness from where it is right now, which is what gives us this dashed line over here, and we can start to reduce it, we can actually potentially increase our mobility from about 6,000 or 5,900 or so up to potentially 10,000 or even 20,000 if we're able to drop our surface roughness from the current value, which is around 2 nanometers or so RMS, down to about 0.5 nanometers RMS. And so what that does is then that allows us to kind of compare some of the work that this templated liquid phase growth enables, and compare it to other deposition, non-epitaxial deposition techniques. And so what you can see is that if we grow indium arsenide and you compare it to polycrystalline indium arsenide, we get a couple of orders of magnitude improvement in the properties. Same thing if you look at our indium phosphide, and again you compare it to polycrystalline indium phosphide, you're getting a couple orders of magnitude improvement. This really comes down to the fact that we're locally controlling the crystallinity, so we can get a single crystalline domain in the area where we have electron transport, so we can remove the effect of one of the most dominant scattering mechanisms in polycrystalline or nanocrystalline materials, which is grain boundary scattering. So this is all really promising. And so then a couple of other questions that we asked is, all right, if we can do this with binary materials, well, what about ternary materials? So we explored two systems here, indium plus gallium, where indium plus gallium, will potentially result in an alloy, indium gallium phosphide, and then indium plus tin, which won't result in an alloy because there isn't any indium tin phosphide. And so when we looked at our indium gallium phosphide, what we actually found is that by controlling the composition of indium and gallium, or the mixture of indium and gallium, we can actually control the composition of the resulting material, which was really interesting and exciting. And it's actually not what we expected, because if you look at the phase diagram, you expect a graded material, but that's not what we got. And the reason that we didn't get that is very likely because the rate at which we were growing the material was fast enough such that we were being pushed off of the phase diagram. So this is kind of nice, but it's also to an extent it's what we would it's kind of expected that you might get either a graded material or indium gallium phosphide when you mix these together. But something else that we found, which was really interesting, is that if you actually mix indium and tin together, what ends up happening is when you grow these, you actually get two separate crystals that have this really nice interface. And the reason that this happens is because when you heat up an indium and tin mixture, and then you start exposing it to phosphorus, as you increase the concentration of phosphorus in the liquid indium, what ends up happening is that indium phosphide is the first material that becomes unstable and wants to precipitate out. And so you get a precipitation, I should say that indium phosphide becomes the first material that's stable and it wants to precipitate out. And so you get an indium phosphide nuclide that then grows out. And when it's growing out, you only get a small fraction of tin incorporated, so just doping levels of tin incorporated in the indium phosphide, and you use up all the indium. And so you get this crystal of indium phosphide. Then what ends up happening is that after that, you're just left with tin in the template, and that tin again gets supersaturated with phosphorus, and then you crystallize out tin phosphide, which is a different material. And then what happens is that those two crystals kind of zip up at the interface. Now this is kind of different from standard heteroepitaxial growth or non-epitaxial growth in the fact that you're not growing the second crystal off of the first crystal, so you don't have the same strain boundary condition issues that you do when you're growing, a few layers of, say, tin phosphide on indium phosphide. What actually happens is you're growing, an entire crystal, and that crystal is kind of then merging at the interface between these two, and so you get this really nice. This is a high-res TEM image, and you get this really nice interface between two materials that have totally different crystal structures. Now, we've taken these materials and we've made various electronic devices out of them. So things like MOSFETs, synaptic devices, and optoelectronic devices. And mostly we're doing this to kind of show that, not only can we grow these materials and characterize them, they're useful for, they're device grade, they're useful for devices. And so that's a really quick summary of our work in the device area, in the materials and device area, focusing on our materials work. And basically we have this approach to grow crystalline 3,5s on non-epitaxial substrates. We've been able to do it at lower temperatures and still show promising results in terms of the mobilities and the optoelectronic properties. And then also when we look at the electronic device, when we look at devices, we can make useful devices out of it. Now, going forwards on the material side, we're actually, we also have an MOCVD, and so we're doing this mixed growth where we grow crystals and then we grow use MOCVD and grow on top of that. And so that's kind of where we're headed here. So with that, now I'm going to switch gears, and I'm actually going to talk about our non-equilibrium electron work. So it's going to be a little bit of a shift here, but basically the thing that I'm going to talk about for the majority of this is our work on electron emission. And because I come from a certain background and I've moved into this area, I want to put one slide up to say, well, why do we care about electron emitters? And it turns out that there's a wide variety of places where these are still used. But in my research, in terms of the people who fund me, there's two reasons that they care about it. And so there's two reasons I care about it. The first one is accelerators, and that's specifically for DOE applications. And the second one is vacuum electron devices, which is AFOSR and ONR applications. And specifically, I'm going to focus on the vacuum electron device perspective. And the whole idea behind what I'm working on here is, can we build new types of electron emitters to potentially be ultra fast and potentially address higher frequency, higher power output, HPM, high power microwave or vacuum electron devices. That's kind of some of the stuff that I'm looking at and we're trying to understand. There's a few things that you need. You need high speed. You need them to be compact and stable. You need them to be bright, although using the term bright here a little bit incorrectly, but basically high current levels. So what we were trying to look at here and trying to understand is trying to understand, and I do see some questions, but I understand that I'm going to answer them at the end of the talk. So I hope that's okay with everyone. That's my understanding of how the structure of this is. So here, what we're looking at and we're trying to understand is, could we do something with photoemission? Where we shine light on something and then excite an electron and have it come out. And so then we can look at the general mechanisms of photoemission. And you have your standard photoelectric effect, where photon comes in, it's got so much energy that an electron gets excited to a higher energy state, and that in that energy state, the electron has enough momentum such that it can overcome the work function barrier and just pop right out into free space. There's multi-photon electron emission, where a single electron gets excited twice or multiple times by incident photons, where and then it gets kicked up to a higher energy state. It has enough momentum, it can be emitted into free space. And then finally, you've got strong field emission, where it's the electric field of the photons themselves, which actually cause field emission of the cold electrons in the device. And one of the challenges with photoemission, especially for vacuum electron type devices, is that if you want stable single photon based electron emitters, which are they're great, they're very high efficiency, not very high efficiency, but they're relatively high efficiency. And if you're using copper or something like that, they're relatively stable. But the problem is you need pretty high photon energies to be able to excite your electrons above the work function of these metal emitters. On the other hand, you could say, all right, well, I'll drop down my photon energy so I could potentially use smaller, more compact lasers. But then the problem becomes you need really high photon flux to actually drive these. And so again, what ends up happening is that these are really not compact solutions. We were asking, well, okay, can we try something slightly different where we actually say, hey, let's let's do what some have called in the past photo field emission, right? Where we take a photon, it comes in and excites an electron part way, and then it tunnels out through field emission. And we said, all right, if we want to build a device that does that, can we, is this even something that's accessible? Meaning, do the relative rates of emission and scattering, do these processes even give you any options or opportunities here to do this? And so in order to understand that and think about what type of device we might want to build, what we actually said was, all right, let's think about the process here, right? So what happens is you have some material, and I've got a little cartoon sketch on the left-hand side of energy versus position, and there's an emitting surface over here. What's going to end up happening is a photon's going to come in, it's going to excite an electron from somewhere below the Fermi level up to somewhere above the Fermi level. That electron's going to get transported to an emitting surface. And if there's a high enough probability of emission at that emitting surface, it'll be emitted. And so what ends up happening is you get this competition between electron transport and tunneling into vacuum versus electron scattering. And so what ends up happening is that we need to find a device structure that allows us to somehow prioritize electron emission versus electron scattering. And just to kind of put things into perspective, this is a calculation that we did for graphene, but what it's showing here is if you inject individual electrons into graphene at about 1.5 eV above the vacuum level, above the Dirac point, and then you plot the average energy of those injected electrons, you know how fast they lose energy. So you can see that you lose about 1 eV of your excited energy in about 300 femtoseconds. So what that says is that these relaxation processes are very, very fast, and they're a challenge to fight against. So what we said is, all right, let's build a device that looks like this, which is single layer of graphene, so that anytime there's an excited electron, you're already at an emitting surface. Put it on a waveguide so that you can just improve the absorption, right? So because if you have a two-dimensional material, your absorption is relatively low. We don't want 2% absorption. That's a couple of orders of magnitude of loss right there. And then also, instead of using a metal tip, if we use graphene, there's no transport to the surface required, and also you tend to have slightly lower scattering rates or energy loss rates due to the fact that there's lower densities of electrons to interact with. Because electron-electron interactions can cause a tremendous amount of, even though the scattering rates might be lower than electron-phonon interactions, they can cause the per scattering event loss is going to be very high, and so they can cause a lot of energy loss. And so then, the basic process, the basic idea here, it's not too complicated. We have, our graphene over here. This is just a cartoon of the graphene band structure. We send a photon in, we excite an electron across the Dirac point. That electron can then scatter down and just thermalize. Or if we apply a field to the surface, we can just pull it out, meaning that electron can be emitted. So then we built this device. These are just some images showing the fabricated device and some of the characterization that we did. But this is kind of the key data, is that what we did is we took that device and then we applied a field orthogonal to the plane of the graphene. So we're pulling electrons out orthogonally to the graphene. And then what we can do is we can measure the electron emission as a function of this applied field. And then we can do it with light in the waveguide and without light in the waveguide. So what you're seeing on the left-hand side is that, basically this is the dark curve over here. And this dark curve, essentially we have our baseline, which is just our measurement baseline. This is just the noise from our tool. And then at about 3 to 3.5 volts per micron of applied field, we start to see cold field emission from the device. And then on the other hand, if we turn on the light, meaning we shine light into that waveguide, we inject light into the waveguide, what we actually see is that we get some considerable change in the emitted current below this cold field emission threshold, suggesting to us that it's due to hot electrons. And then if we park our voltage right around here, and then we modulate the optical power, we see that the current versus optical power is linear, again suggesting it's a single photon process. So then what we do is we compared it to some of the literature in using strong field and multi-photon emission by focusing lasers, pulsed lasers onto metal tips. And essentially what we see is that we get emission at much lower power densities here. And that's because we're trying to highlight the fact that we're working with a different mechanism than we would be working with if we're doing multi-photon excitation, or if we're doing strong field emission. And so we're using this to say, hey, this is evidence that we're actually working in this hot electron emission regime that we think we are. But we needed to spend some time modeling this behavior and really trying to understand what's going on. And so in order to do that, what we did is we said, hey, well, we have two populations of electrons that emit, basically. You have your excited electrons, your hot electrons that will emit, and then you have your cold electrons which will emit. Let's build a simulator and try to understand the crossover between these two cases. So what we did was we basically built a two-dimensional graphene Monte Carlo Boltzmann transport simulator. We implemented electron-electron scattering, optical phonon scattering, and collisional phonon scattering. And then we took that and we tried to fit other people's experimental data, people that we didn't know and had no relationship. So we tried to fit their experimental data, the pump probe, and kind of steady state carrier heating data, so that we could try to understand if this was reasonable And what we saw is that our simulator was reasonable at reproducing other people's experimental data. So we said, okay, let's then try to use it to understand our data. And again, we're trying to understand two different, mechanisms here: the field emission, the cold field emission, and the hot electron emission. And so what we ended up with is, if we look at our experiment, we get a crossover between hot electron emission to cold field emission at about 3.5 volts per micron, and the current is about 100 picoamps. And our simulation, our crossover field, our predicted crossover field is about 3.8 volts per micron, with a crossover current about 50 picoamps. And basically we did not fit the simulator to our data. We only used our work function and our field enhancement factor extracted from the dark curves for this. So kind of told us that, hey, this is this mechanism that we think is happening. It's reasonable. But one of the problems is these current levels are really low. They're not really useful for vacuum electron devices. This is more of a proof, an existence proof that, hey, this exists. It can be potentially utilized. So then what we did is we did some theoretical work, and we said, hey, where could this potentially go, and how fast could it be? And what we're showing in this central graph is basically the current density as a function of absorbed power density. And this is where we're sitting over here. This is our experimental data. And then what we kind of see is that if we can go from where we are right now to pushing it up to about, say, 10 to the 8, 10 to the 9 watts per meter squared, which is reasonable for an optical cavity, we can actually start to get current densities, which are of use for vacuum electron devices. But the really interesting thing is, if we actually plot our response times, meaning if we hit it with an impulse and we look at how long it takes for 90% of the current to decay to 90% of the original. In that case, this is how we're defining it. What you can actually see is that we can get sub-picosecond response times, which potentially allows us to make really fast devices. And so, we're saying that this is potentially something that allows us to kind of address some of the challenges that we said before, in terms of speed, compactness, brightness. Stability, it's reasonably stable, meaning in the sense that for these devices, because they're graphene and we're just shining light on them, in a vacuum, they seem to operate reasonably. We haven't put them in an actual device, so we don't have data for that. But these are also just stored at in ambient conditions. There's nothing fancy about them. And so this is kind of a quick summary of what we've done here. We've shown these hot electron emission devices. We've done some modeling, shown the limits of performance, and kind of when we think about the outlook of this, what we're doing now. And actually, this is something we just got an ONR Young Investigator Award for this, where we're actually going to take optically modulated cathodes. So we've been working on this technology and also some other technologies for optically modulated cathodes. And then the whole idea would be to take a signal that's in a laser, convert it to the same signal in an electron beam, accelerate that electron beam, and then interact that accelerated electron beam with some cavities to pull the basically to generate electromagnetic energy by pulling energy out of the electron beams, out of the higher frequency components in the electron beam. And so then the last thing, which I will only briefly touch on because I should leave some time for Q&A, is that we also do some work on non-equilibrium electrochemistry, where instead of exciting electrons using photons, what we do is we build MIS type devices, so metal insulator semiconductor or graphene insulator semiconductor type devices. And then we apply a field between the metal or the graphene and the semiconductor, and we actually just inject electrons from the semiconductor into the graphene or the metal, and those injected electrons, depending on the voltage between the graphene and the metal, can come in at energies that are pretty hot compared to the Fermi level of your metal or your graphene. And so we build these devices, we stick them in an electrochemical solution, we do the measurements. This is actually on gold, but something that's kind of interesting is that what we're showing in this orange curve was the hydrogen evolution reaction. If we just applied a voltage between our gold electrode and our solution, and then if we just repeat that measurement, but we turn on the metal insulator semiconductor diode behind the gold, such that it's injecting hot electrons into the gold, we actually see this shift, which we're claiming is due to hot electrons. And the thing that's really interesting about it is that if we looked at the quote unquote quantum efficiency, meaning in terms of the current that was injected from the semiconductor into the gold versus the change in the current from the gold into the solution, it seems to actually be pretty highly efficient, which is kind of neat here. So this is also something I would say it was a little bit unexpected. We also did some modeling for this using our same Monte Carlo Boltzmann transport solver, just to show that if you look at the interaction rates of hot electrons with the surface of the gold and the solution, you actually did see a significant change in that those interaction rates at higher energies. So suggesting that there was some active population of electrons interacting with the surface at energies above what you would expect just from the Fermi distribution and rates that you would expect above that. And we also did this with graphene, and we found that we could again get these pretty nice shifts over to lower applied voltage for the hydrogen evolution reaction, and it was a little bit better than our gold devices. And something that was actually particularly interesting about the graphene is that we got a lot of modulated, what we call direct injection current, where essentially the silicon electrode was injecting electrons both into the graphene and into the solution at the same time, and it was doing it almost through parallel channels. And so, again, really quick conclusion for that is that we built these devices and we showed some electrochemical, we showed some modifications of the electrochemical reaction rate. And with that, I'd like to acknowledge my PhD students. I've had a lot of really great PhD students, current as well as former. Most of the work that I've been talking about was driven by one of my PhD students, Debargia Sarkar, and another one, and that was most of my material work. And my electron emission work was mostly driven by Dr. Fatemeh Rezai, were two of my first grad students, and were very successful and really worked out well for me. And our work has been funded by a variety of organizations, depending on the application. And so with that, I would like to open up for questions. Thank you.
Thank you, Rehan, for a great talk. So we have a few minutes for questions, and I already see a few, so I'm going to read them out to you. But to our audience, feel free to type your questions, or if you would like to directly ask your questions, you can also raise your hand. So the first question is asking, for your templated growth, you showed examples where you had your material vertically stacked. What if the indium and tin is side by side before the growth?
So the short answer is it won't matter. The reason for this is fundamentally because we're depositing them through evaporation. So when we stack them vertically, yeah, it's stacked vertically. But once we heat it up, the indium and tin basically just become an alloy, or the indium and gallium, it just becomes an alloy. And so whatever original geometry you had is going to be lost, and it's just going to stay in that in the template geometry that you have. So you can imagine you just get some alloy of indium and tin, or indium and gallium, depending on the original relative thicknesses.
So to follow up on that, how well can you control the thickness of the layers that you form, or how would you do it?
So yeah, that's a great question. And so the control of the thickness purely comes down to controlling the initial evaporation, the initial thickness of the evaporation. And it's actually pretty straightforward, especially at thicker layers. When you're getting down to like the 10 nanometer type range, you have to consider how wetting of that material works, and it's a little bit more tricky at that scale, but it is doable, depending on the size of the templates that you want, and depending on the substrate. So, for example, if you're growing on metals, you can kind of have an arbitrary thickness because the way that the surface energies work out, it doesn't de-wet when you have your capping layer on there. When you're growing on oxides and nitrides, it's a little bit more complicated, and we've worked out the details of this in one of our papers. But basically, it kind of depends on the relative ratios of the thickness of the material and the width or the scale of the size of the template.
Thank you. So the next question, Bruce is asking, could the electron emitters be used for X-ray coherent sources?
You know, I have a proposal out with someone else right now for that application. It hasn't been funded yet. I don't know if it will be funded, but yeah, I think so. Do I know so? No, not yet. But I'm asking for money to try to see if that would work. It's a great question. You know, it's a great question.
Great. Yupeng is asking, how was the fiber inserted close to the wave?
That's a good question, and I'm actually gonna, you know what, to answer that, I'm just gonna go back to a picture that I just quickly glossed over. So okay, so this left-hand image is an optical image of the silicon surface with the silicon nitride waveguide and graphene. What you see over here is a U groove that we dry etched into the silicon, and then what we do is we actually take some epoxy, we put it on the fiber, stripped fiber, and we put it in there, and then we see the light, we couple the fiber into the waveguide, so it's coupled into the waveguide, and then we let the epoxy dry, and so it holds it in there, and then we stick that whole thing into a vacuum chamber, because obviously it's electron emission, everything's done in a vacuum chamber, so high vac chamber. So that's the answer to that. It's a good question. I mean, it's actually a technological challenge, and it's really annoying to have to work it out, and especially to have to work in a vacuum chamber, because all the technologies people use to couple fibers into on-chip stuff is not really. It's you can't have any free space fibers. We can't be aligning anything. Can't do that. So.
So Matthew is asking again about your templated growth. Have you been able to find a way to control the crystal orientation of the templates?
Yeah, that's a fantastic question. So basically, right now, the way it works is we tend to get the vertical face tends to be 1, 1, 1, but we don't really have control on the lateral dimension. There are potentially ways that we've thought about trying to control it in terms of structuring the underlying substrate. But so far, we're really focusing on trying to make large single crystalline areas with the idea that we can make an entire area to be a certain crystal orientation. The devices that we would make on that area would all have uniform properties. And so, the goal is to be able to make millimeter scale templates. The only challenge with that is it takes longer time. It takes a longer growth time. But that's kind of just a natural consequence of the physics of how these things grow.
Thank you. So this next question is asking, what are the advantages of using zirconium oxide instead of aluminum oxide?
Okay, and I guess this is you're probably asking about this from a tunneling perspective for the electrochemical devices. And so, so to answer this question, maybe let me see if I don't think I have a good picture here. Okay, so that's fine. I'll just stick with this picture over here. This is a cartoon band diagram, so it's obviously super inaccurate. But essentially, if you have a device like this, right, you have a standard MIS capacitor. We have ways of modeling those. Now, and especially in terms of how much voltage is dropped across the oxide versus how much voltage is dropped across the semiconductor. Now, the thing is that when you actually have current flowing across the oxide, what ends up happening is it's almost like you have resistors in series. So what happens is the amount of voltage that gets dropped across the oxide versus the amount of voltage that gets dropped in the semiconductor, it's going to be a function of the current. So you're going to have a continuous current across the two, And you have to have a certain field across the oxide to generate a certain amount of current across the oxide. And that field multiplied by the thickness of the oxide is going to give you the voltage dropped across the oxide. And then the rest of it tends to, go into the semiconductor. So now, to generalize your question a little bit more beyond just zirconium dioxide and aluminum oxide, it is that as you go as you use different materials, what ends up happening is you have different tunneling barriers, and those different tunneling barriers will lead to different relative distributions of the voltage dropping across the oxide versus the semiconductor, which will then lead to different levels of hotness of your electrons, which are being injected into that top surface. So the answer is it does matter, and we can model it, but the reality is that you have to consider the fact that the tunneling models you use tend to underestimate the effect of your non-ideal tunneling rates, like trap-assisted tunneling and whatnot, which really reduces the amount of voltage that gets dropped across your oxide, which really reduces how hot your electrons are when they're injected into this material. Sorry for the convoluted answer to your question, but there is no simple answer as far as I know right now, anyway.
Great, thank you. So one last question. How large is the electron scattering loss with an applied field that leads to hot electron emission? Is there a theoretical limit on how much you can suppress electron scattering losses?
That's a great question. Actually, I'm going to go to a cartoon picture here because it will help me understand. It'll help me. I think this cartoon picture is really important here because it kind of helps frame this question. So essentially, right, I mean, ideally, if we didn't have, if our cold electrons were really far down in energy, then what we could do is we could just keep applying a higher and higher field. And by continuously applying a higher field, eventually we would get it such that these hot electrons would have a unity probability of, or the rate of tunneling would be significantly higher than scattering. So then every excited hot electron would be emitted. Now, the reality is you can't do that because there is a size of the population of hot electrons, and there's a difference in energy between your cold electrons and your hot electrons, which means that at a given excitation power, there is just a certain applied field at which your cold electron emission will totally dominate your hot electron emission. Nothing you can do about that. That is kind of what sets the how well you can adjust the relative rates of electron emission versus electron scattering. Now, in terms of suppressing electron scattering, frankly, I don't know the answer to that. I think that if there are ideas of how we could suppress electron scattering in these materials, I'm very open to it. I would love to know how to do that. But we're really playing with the other side of the equation, which is the electron emission rates. But because of the basic principles of how this device works, there are some limits there. I wouldn't call them fundamental limits, but they're real limits that just come from the fact that you have a certain energy difference between your cold and hot population. Your cold electrons, and I shouldn't say a hot population of electrons because the density of photons that we're using here is so small that you don't really have this huge population of hot electrons. Essentially, you're exciting an electron, and that electron is either going to be emitted at its highest energy or it's going to scatter back down because the relative rates of emission are they drop extremely fast with energy. So that's again another convoluted answer to a simple question.
Wonderful. So we're out of time. Thank you very much for being here today for a very interesting talk. We enjoyed it very much. We had quite a lot of comments thanking you from our audience as well. So thank you for a wonderful talk.
Thank you, and have a good one.
Awesome.
Bye-bye.
And to our audience too, thank you for being here today. This was the last seminar for this year. We'll see you back in September. Thank you.